Physics Notes, Unit 18C, Part 2, Electric Fields. Once again, an electric field is the space that surrounds an electric charge. And here's three charges, so there are three interacting fields that would be difficult to draw. Each one individually would be easy to draw. The one around the 3 microcoulomb charge positive would be just like kind of like drawing rays out of the sun. That's at the very top of the page of notes here, where you just have force lines just going radially outward. In fact, each one of these individually would look like that, just radial lines going out or in. These two would be, this one would be in, all lines pointing in, like the opposite of the rays of the sun. And this one also would be inward. But when you have three of them, especially three that are different, the field would be really, really hard to draw. So we're not going to do that. But what's nice about this one is it's a pretty easy vector problem in a sense. There's a little bit of work to do, but these are collinear lines, so it makes the problem, a vector problem, just a simple addition or subtraction. You still got to pay attention to the vectors. But there's going to be three computations. We're just going to calculate. Let me get, well, let me draw this out. Here's the equation, the basic equation for electric field for a point charge, and that is E equals K. Well, usually we use lower. I could use capital letter Q, but KQ over R squared. We also have the definition, which we're not going to use right now. E equals F over Q. We'll be using that again in a little bit here. But we're going to do this equation 3 times and then add up the results. For example, just do them one at a time. Let's start with the 3. The 3 microcoulomb charge would have lines pointing in towards it. It would have lines pointing in. I'm sorry, out, because it's always away from a positive. Like the rays of the sun. If like the 3 microcoulomb charge with the sun, you'd have outward lines, and that one line going to the right would then go this way. I'm going to call that E3. E sub 3, meaning the field as that little piece of that 3-dimensional field or 2-dimensional field that's outward from the 3 microcoulomb charge. All I care about is how strong it is right there at that point, pointing to the right. For the 6 microcoulomb charge, it's towards that. All right, it's towards that one. So that's going to be E, I'll say 6. It's going to be stronger because I'm closer. It's twice as strong just because of it's twice the charge, and it's closer as well. So it's going to be stronger for 2 reasons. And then for the 9 microcoulomb charge, once again, the spot, I'll highlight the spot, the dot instead of an X. For the 9 microcoulomb charge, there's also a field towards that one, which is going to be strong as well. E9, because you're close. So there's 2 fields that are towards the right and one that's towards the left. So I'm going to be adding 3 plus 9 and subtracting 6. And it's just a matter of doing those 3 computations and then combining those numbers like we just said. So for example, I'll come over here to the left. E3 is just going to be 9 times 10 to the 9th times 3 micro. Remember, that's 10 to the negative 6th. Over, what is the distance? It's 0.30 squared. So if you plug all that into your calculator, it comes out to be 3.0 times 10 to the 5th newtons per coulomb. Then E sub 6 is 9 times 10 to the 9th times 6 microcoulombs over, now you're 20 centimeters. 0.20 squared. So 9 times 10 to the 9th times 6 times 10 to the negative 6th. Do that first, and then divide by 0.20 squared. Divide by 0.20 twice. And you get a bigger number. It's 13.5 times 10 to the 5th. Now I put that in non-standard scientific form because I want to be able to combine that with the one above it. I want the 10 to the 5th to be the same for both of those. So when they both have a 10 to the 5th, I can combine those, add or subtract if I have to. If I add them, it's 16. If I subtract, it's 10.5. Those are going to be subtracted eventually, but before I do that, let's get the third one in here. 9 times 10 to the 9th times 9 micro divided by, it's still 0.20 squared, it's the distance. It's going to be slightly bigger than the 13. It's 20.3 times 10 to the 5th newtons per coulomb. And the directions are all taken care of. Once again, you don't put any negatives in these equations. There's three distinct separate fields that are combined to give you one field, but the total field, E total, if I look at the diagram, will be E sub 3 plus E sub 9 minus E sub 6, because E sub 6 is to the left. So it's pretty simple in that case. Ignoring the 10 to the 5th for a few minutes, because they're all 10 to the 5th. They got to all be the same exponent of the 10. So I have E3, which is, I'll just put down 3.0 plus 20.3 minus 13.5. Those are all times 10 to the 5th, just to make it simple for us right now. So I don't need a calculator. It's 23.3. 23.3 minus 13.5. So that comes out to be, what, 9.8 times 10 to the 5th. Put that back in there. Newtons per coulomb, and the answer is to the right. The direction is important as well. So that's the net field, electric field, at that location. Once again, there's nothing there. It's empty space. That's the force per unit of charge that would be on a charge. If I put a 1 coulomb charge right there, the force on that charge would be this force. If I put a 2 coulomb charge there, it would be 2 times that, because that many newtons per coulomb of charge that I put at that location. I just wouldn't put those big. Those would be huge charges. They'd be bigger than the sources, so mess it up. But so you wouldn't put that big of a force or charge there. But that's the idea. It's that many newtons per coulomb. All right. This is a similar one to a force problem we had earlier. Let me draw the diagram. And it's asking me to figure out the location where the net electric field would be 0, which would also be the same spot where the force would be 0. But I don't need to do that right now. We did a problem like that before, but it's a similar argument here. I always like to start looking at between the two charges. Is there a spot along, so I'm thinking of a line here, a line that joint, I'm just in my mind, I'm drawing a very dashed line along here. Is there any spot along there where the electric field would be 0? There's nothing there. Well, for example, if I take a spot like midway between the two, I'm too close to the bigger charge. So if I go a little bit left of center, let's just go right there. I'm going to erase everything but that X. Okay, I'll put the X back in there in a second. So I was thinking of that dashed line. I erased most of it. But if I go a little bit left of center, if there's a location right there, because this is going to be the rough location, because the negative 32 microcoulomb is going to have an E field this way. I'm going to call that E32. And then the E52 is this way for the electric field due to the negative 52 unit charge. So you're always towards the negative. So you're towards the 52 and towards the 32. Now, they can be equal here. We have to make them equal but they have to be closer to the 32. Because if you were dead halfway between these two charges, the field from the 52 would be stronger just because it's a bigger charge. Because the field also depends on the size of the charge and the distance. So this one actually, it starts off kind of difficult, or maybe scary. Here's the equation we're using. But what I need to have at that location, that blue X on that diagram, I need to have E32 equal to E52. All right? And E32 is going to be K times the 32 microcoulombs divided by, the distance. I'm going to call the distance X squared. Okay. So let me label that. So this distance right here, from the 32 to that X, that blue X, I'm going to call that, I'll make a dot right there instead of an X. I don't want you to be confused about X's. The X I was just using for location. So I'm looking at that location, that red dot location. It's at a distance of X from the 32. Well, I could call this distance Y, but I know, I didn't tell you yet, the total distance here is 44. You need to know that. Once again, it has to be given. 44 centimeters. Okay. So D is given. D equals 44 centimeters given. If you weren't given that, you can't do the problem. Okay, you would have to do it in symbolic terms, which we're not going to do. But bottom line is now that the distance from the red dot right here to my 52 will be 44 or 0.44 meters, 0.44 minus x. That's how far it is if I draw that line right there. Because the total is 44. If I take 44 minus x, that's the distance from the 52 to the red dot. All right, so if I go back over here, k times 52 micro divided by the distance now. Once again, I could have called it y squared. Then that gives me two variables. But in meters, it's 0.44. I actually could have left it in centimeters. And the answer would come out in centimeters. But I like to stick with standard if I can. But it would, you just would have left that in as 44. The answer would come out in centimeters. But anyways, once again, kind of like that problem we did in the last notes, or a couple pages of notes ago, and I think it was in 18b. The micro cancels out because you have it on both sides. The k cancels out because you have it on both sides. So what you have right now, it's not as hard as it looks. It's not as hard as it looks, especially if you've been through it once. You got 32 over x squared equals 52 over 0.44 minus x quantity squared. So I'm going to take the square root of both sides. I'm going to take the square root of both sides. I'm going to take the square root of the 32, so I'm going to come up here. Square root of 32 is 5.7, 2 sig figs. So I get 5.7. Square root of x squared is x. Square root of 52 is 7.2. 7.2. That's 7.2 over 0.44 minus x. Then I cross multiply, I get 5.7 times 0.44 minus x equals 7.2x. 5.7 times 0.44 is 2.5. Running out of room again. Minus 5.7x equals 7.2x. All right, I'm going to have to go back. This is, I don't like doing it like this, but I would be going down the page. I should have made more room. Hopefully you got room. You just keep going down the page there. Add 5.7 to both sides. So I'm going back up the page. 2.5 equals, what is that, 12.9? 12.9x. And then you divide both sides by 12.9, you get x equals 0.19 meters, 19 centimeters. To the right of the negative 32 microcoulomb charge. 19 centimeters. That's where the electric field would be 0. And that's where the force would be 0. There'd be no force. You put any charge there, the force would be 0 at that location. All right. Ooh, the Millikan Oil Drop experiment. Famous experiment to figure out the charge on the electron. It really was the charge to mass ratio, but it's a short step away from figuring out the charge of the electron. And it's a famous experiment by Robert Millikan. And what he did, all these red dots at the top represent oil droplets. And what he did is he sprayed like a spray bottle with oil drops, spray bottle. And he had like a plate up here with a hole in it. And some of those oil drops would fall through this hole right here into this chamber where he had like a viewing scope, telescope, a viewer where he could see the oil drops fall through, and they would fall through here. But some of those oil drops, just by virtue of spraying them through the bottle, would pick up a charge. And what he did is then these blue discs are parallel plates. They're not rectangular, but they're parallel plates. And he would say make the bottom one negative. He could make it positive, but if you made the bottom one a negative charge, you put a negative charge on here. And then the top one plus charge. They say it has a potential difference. We'll talk about that next chapter. But put charges on those. All right? And once again, there's an electric field there from top to bottom. So that doesn't really matter. But what happens is if an oil drop comes through there, gravity's trying to make it fall. But if it's got a negative charge on it, the negative charge is going to repel it. So the free body diagram for an oil drop, here I'm going to go off to the right here. If this is the oil drop, it's the oil drop. If it's got a negative charge on it, okay, first of all, gravity's trying to pull it down. Force of gravity, F sub G. If it's got a negative charge zone, that bottom plate is negative, then there'll be an upward force, force of E. And you could suspend and you could change how much charge you put on the bottom plate and the top plate. So he had like a machine, a voltage source that he could vary to make the bottom plate more negative or less negative. Or if the drops were positive, you can make the bottom plate positive, but you don't need to do that. This is sufficient here. If you know you got a negative drop, which I think maybe most of them were, the bottom plate's negative, you can suspend it. You can suspend the oil drop there. But you need to know the mass of the oil drop. So for some reason he knew or could figure out the mass of the oil drops based on how big they were and the density of the oil and so forth. It's quite a small mass there. Now here's something interesting. Okay, first of all, well, it's something we haven't done yet. Here was the first thing we did in Unit 18C, the page of notes before this, the definition of electric field strength. E equals F over Q. Well, if E equals F over Q, then if you solve that for F, F equals EQ. And we're talking about electrical force, F sub E. That's that up arrow in that diagram. The electrostatic force equals EQ. Now I also know that force of gravity equals mg. Weight equals mg. That's how you figure out the force of gravity. In this diagram then, in that free body force diagram, I want F sub E equal to F sub G to suspend the oil drop, to keep it stationary. All right, well, I just need to have then, I just plug in EQ. I'm plugging in this for F sub E. And force of gravity, I plug that in, equals mg. So I plug in the two values for those. And if I solve for Q, I could do that now or later, I'll do it now. In this problem, I know M, I know G, and I know E. Let me plug those numbers in. It tells me M is 1.11 times 10 to the 15, negative 15, very important, negative 15 kilograms. We want kilograms. G is 9.8. I'm going to use a little bit more precise number this time. You could use negative 9. Well, no, don't use negative. But I wouldn't use the 10. And E, it tells you it's 22,700, well, kilo, 22.7 kilo newtons per coulomb, which is 22,700. I'll write that out. It's 22 times 10 to the third, 22.7 times 10 to the third. Those are standard units now, but I had to convert into, I got it, that kilo. I had to multiply by 1,000. So if I do the math there, I multiply those two top numbers, divide by the 22,700, it comes out to be 4.8 times 10 to the negative 19th. 4.8 times 10 to the negative 19th coulombs. That's the charge on that oil drop. Well, but we're looking for how many, it says how many excess electrons. Well, each electron is 1.60, way over here to the left, times 10 to the negative 19th coulombs. Some of you can maybe see this. If I take 4.8 times 10 to the negative 19th divided by 1.6 times 10 to the negative 19th, that's 3. There's 3 electrons. 3 electrons. In other words, it takes 3 electrons to make 4.8, because 2 electrons would be 3.2 times 10 to the 19th, and then 3 of them is 4.8. Basically, he didn't know the charge of the electrons, but when he did this, the basic idea of his experiment, it's more complicated than this. It probably took him years to do this, but he was a famous he's a famous scientist because of this. He did it over and over and over and over and over again. And, he had to build the apparatus and everything else, and he probably had trial and error and trial and error. But bottom line is he did this over and over and over again, because if there's 4 electrons on there, then it's going to be, 6.4. And if there's 2 electrons on there, it's going to be 3.2 times 10 to the negative 19th. What he noticed is that when he did this and got all this experimental data, he found out that the least common multiple is the 1.6 times 10 to the negative 19th. That's how he figured out, because everything has to be a multiple of that. And he had some bad data in there as well, so he had to sort through all that. But in the end run, he could figure out that the least common multiple, or the is the 1.6. I always forget, least common multiple, or actually greatest common factor, or the common factor. The least common factor, 1.60. I'm not sure I'm saying that right, but the common factor for all of those, 1.6 times 10 to the 19th coulombs. They were all a multiple of that number. That's the number he figured out. Or the ratio of that to the mass of the electron. Okay, here's another one. This is, well, J.J. Thompson did an experiment like this. This is not quite Thompson's experiment. It doesn't really matter. But this is a good review question. It incorporates some things from Physics 201, uniform acceleration. I've already mentioned that. We're going to be doing some more of that in the next unit as well, in Unit 19. We have 2 plates here. We have an electron going across, and it enters this field, and there's 2 plates here. Once again, kind of like the Millikan experiment, basically. 2 plates. I mean, they could be round discs, one above the other, and they're horizontal. And you're shooting an electron through there, and the electron is then, once it goes through there, it's being repelled. It gets repelled upwards towards the ceiling, so that this top plate is near the ceiling, in the direction of the ceiling. This one's the direction of the floor. Gravity wants to pull this thing down. So once again, as that electron goes through there, as the electron goes through that field, gravity wants to pull it down, force of gravity, and the electrical force is going to be very similar start to the last one, where we want, so in this case, though, we're going to do F net equals ma. We want to do F net equals ma because we want to figure out the acceleration of this particular particle, because there's no forces left and right. It's kind of like a projectile problem, but in reverse, where it's going to kind of curve upward, because there's going to be the electrical force is going to be greater than the gravitational force. Well, I'm pretty sure of it. It tells you the mass. I know the gravitational force is going to be the gravitational force is mg. So the gravitational force is the mass, which is what, 9.11 times 10 to the negative 31st times, I'm going to use 10 this time just to show you that it's inconsequential here. It's insignificant. The force of gravity basically is going to be 9.11 times 10 to the negative 30th. Real close to that. 9 times 10 to the negative 30th newtons. But the electrical force, like in the previous problem, once again, if we resolve that, E equals F over Q. In other words, the electrical force, just like before, is E times Q. In this problem, whoops, I want the electrical force. It turns out, if you look at this, because we're not trying to suspend, we're not suspending this one. It's going to accelerate. We don't want the electrical force. Well, we could have the electrical force equal to gravity force, then it would go straight through. It wouldn't be deflected up or down. So I guess that would be a question, how strong does the electric force need to be to offset gravity? Would have to be that 9.11 times 10 to the negative 30th. I could put that in there right now. If I put that number in for force right now and plug in the Q, the charge of the electron, I can figure out what field I need so the electron doesn't curve down because of gravity and doesn't curve up because of electrical force. But in this case, they're telling me the electric field is 120 newtons per coulomb. So we got, this is such a large number times the 1.60 times 10 to the negative 31st kilograms. All right. No, not kilogram. Not that's wrong. 1.60 times 10 to the negative 19th. 31 is the kilograms for mass. So the electrical force, right, is the given 120 times the 1.60 comes out to be 1.92 times 10 to the negative 17th. 1.92 times 10 to the negative 17th newtons. Let me just circle that for a second, because I'm trying to compare these two numbers to figure out what the F net. If they're equal, then there'll be no net up and down force. The electron will just shoot through this gap and not go up or down. But F electrical up here that I just calculated, I'll highlight F sub E, 1.92 times 10 to the negative 17th. Seems awful small, but it's way, way bigger than 9.11 times 10 to the negative 30th. This one here is insignificant. It's insignificant. I can't really add or subtract it to the 1.92. So the net force is really the electrical force. It's really the only significant force. And then if I have, okay, so F net equals MA, well, the electrical force is the net force. Subtract that 9.11, it doesn't change it. The net force is the upward force. 1.92 times 10 to the negative 17th equals the mass. Now we have the mass, 9.11. 9.11 times 10 to the negative 31st. That's the mass of the electron times the acceleration. So it's going to accelerate up instead of accelerate down. It's not going to accelerate down at 9.8. It would if gravity were anywhere near the other force, or if there wasn't the other force. But the acceleration is 2.1 times 10 to the 13th. That's a huge acceleration. 2.1 times 10 to the 13th meters per second squared. That's going to be an acceleration upward. Not the final answer, but I like to circle the important answer, important numbers. Now, here's the thing. This is kind of like a projectile problem, except in reverse. The thing is going to curve upward. That acceleration right there is going to be the vertical acceleration. Horizontally, no acceleration. So horizontally, we have V equals delta x over t. And it tells you the initial velocity. It tells you the initial velocity, doesn't it? 3.3 times 10 to the 6th. That's horizontal velocity. 3.3 times 10 to the 6th meters per second. And it says it's going to go through that gap, and the gap is how long, how far? It's 3.9 centimeters. 3.9 centimeters, 0.039 meters. So how long does it take to get to that gap? Well, here we go. It's going to be, if you move things around, it's going to be 0.039 divided by the 3.3 times 10 to the 6th. And that's 1.2 times 10 to the negative 8 seconds. Not very long. 1.2 times 10 to the negative 8 seconds. That's 12 nanoseconds. It'd be 12 times 10 to the negative 9 seconds. Not even a blink of the eye. But vertically at the same time. So this is like a projectile problem. All right. So here's the little trick. So as it enters that space between those two plates, it's only moving sideways. It's not moving up or down, so that's 0 meters per second. That's a little bit tricky. It's not the 3.3. The 3.3 is the sideways. So then we're going to have a V final. We know the acceleration is 2.1. That's the vertical acceleration. That's in the vertical direction because that's the only force acting is a force upward towards that top plate. And it gave us this acceleration times 10 to the 13th meters per second squared. And I know it's going to be acting for a time of that same time, 1.2 times 10 to the negative 8 seconds. And it's going to have a delta y of something we don't know yet. We're actually looking for that. So if you go back to your equations for uniform acceleration, I think the first or second equation, I don't have them numbered. Well, I kind of have them numbered. Equals, oopsie. But I know one of them. I think it's you can go back in your notes from first semester, from first term. But one of the equations is this. For uniform acceleration, Vf equals V initial, which is 0, plus a times t. And the a here is what? 2.1 times 10 to the 13th times the time. I'm going to squeeze this in. I don't know if I'll get it in. 1.2 times 10 to the negative 8th. 1.2 times 10. Hopefully I'm not going off the page here. So you can imagine 10 to the negative 8th. So V sub f, 2.1 times 10 to the 13th times 1.2 times 10 to the negative 8th is 2.5 times 10 to the 5th. 2.5 times 10 to the 5th meters per second. Once again, an important number. When it comes out of that gap, that's the vertical velocity. It's been speeding up. Still has the horizontal velocity. That didn't change. That's the vertical velocity. But I also need, actually, I didn't even look at the questions. That's an important number. The exit angle. I'll get back to that. Part A, the vertical deflection. Really what I got to find is delta y. But let's see here. You can use the, I think it's the fourth equation that says that delta y equals is v sub 0 t plus 1/2 a t squared. So delta y, well, v0 is 0, so it's 1/2 times the acceleration, which is 2.1, times 10 to the, it's 10. I'm still trying to squeeze these in here. Sorry about this, folks. 2.1 times 10 to the 13th times the time squared. No, yeah, time squared. 1.2 times 10 to the 8th. That's a 10. That's 1.2 times 10. Come on, to the 8th. No. I keep messing up. Have patience with me. 10 to the 8th squared. I hope that's on the page. It's 1.2 times 10 to the 8th squared. So delta y equals 1.5 times 10 to the 3rd meters. 1.5 times, this will fit on the page real nice. 1.5 times 10 to the 3rd meters. So that is the vertical deflection. That's how high up it goes from that line. That's actually the answer to part A, the vertical deflection. By the way, that's 1.5 millimeters. All right, I can get it. That's 1.5 millimeters. So on like a regular meter stick, that each line is a millimeter. This is like the diameter of a paperclip. The metal part. I'm going way over here to the right for B, to the left for B. All right, so for B, it's a vector problem. It's a vector problem. When the electron comes out, it's still moving sideways at 3.3 times 10 to the, 6 meters per second. But when it exits, at the exit point, it's moving up at the 2.5 times 10 to the 5th. 2.5 times 10 to the 5th. That was the answer that we got way over here. The vertical velocity it exits at, because it accelerated. So what we're looking for, this is just a basic Pythagorean theorem. So I'm just looking at, I can figure out we're looking for the angle. I could use the Pythagorean theorem to get the actual exit velocity, which is a squared plus b squared equals c squared, but it doesn't ask me for the exit velocity, just asks me for the exit angle. And that would be, to get that, I would use tangent of theta equals the 2.5 times 10 to the 5th divided by 3. Not happy with my writing today for some reason. Hopefully you're more patient. I guess you have no choice. 3.3 times 10 to the 6th. So you're going to divide that and take the inverse tan. You got to hit the inverse tan button to get the angle. So you do inverse tangent of theta equals that ratio. So you divide that out, do inverse tangent. 4.3 degrees. That's the exit angle. There's a homework problem like this. Once again, I love this kind of stuff. I kid around with, well, not really kidding. I tell my students, my first love really was, well, besides my wife, was math. I mean, I love the mathematical part of physics. Some people don't. I like all parts of physics, but particularly doing this kind of stuff, I just feel good when it's done. And this is not a complete mess. It looks a little messy, but I didn't do too bad here. It's readable. So, once again, different things make different people feel. It makes me feel good about myself. I guess, I don't know. That's pretty sad if that's what it takes. No, but this is not that important in life. But I mean, it's important to do things right. Physics is great. Physics is important. I don't want to say it's not important, but there's other things more important than physics, like my wife and relationships and being kind to people and stuff like that. So, but I hope you could follow this. That's a wrap for Unit 18, electric fields. and charging by induction and conduction and charge polarization. So it's a long unit. It's a big chapter, and then we will have we'll be moving on to electric circuits and currents here shortly. So stay tuned. Whoops, I forgot to say, sorry about that. The next unit is electric potential and electric potential energy, then circuits. So a lot to look forward to, a lot of electrical things still in store. Enjoy this unit. We'll see you in Unit 19.